All right, let's start. Good morning. Attendance today. Okay, so we were discussing orthogonal things. We said, oh, I have a vector space, and defined on it, I want to have a thing called inner product. You feed to this inner product two vectors, gives you back one scalar. And then we said, oh, once I have this inner product, I can talk about norms of vectors. In other words, magnitudes of length or lengths of vectors. Then I can talk about the distance between any two vectors. I can also talk about angles between any two vectors. Once I can talk about angles, I can talk about what it means for two vectors to be perpendicular to each other, having 90 degrees between them. Once we have a notion of perpendicularity, we can talk about this orthogonal complement of any set. Now, this week, if you look at the syllabus, it's titled Gram-Schmidt algorithm. And it's essentially a certain algorithm that is associated to orthogonality. Okay. Now, there's some confusing terminology. In this context, pretty much everything is called orthogonal, but they're sort of like different things. So I want to introduce those. I want to finish up this example that I started last week, which was this matrix A, 1, 1, 0, 0. I wanted to relate the null space and column space of A to the null space and column space of A transpose somehow. And so I said transposes have to do with perp operation. And this is going to lead us to the second version of the fundamental theorem of linear algebra. If you like watching lectures on YouTube, Gil Strang at MIT OCW has this famous linear algebra course for engineers and stuff, and he calls this whole business the four important subspaces that one needs to know. It is indeed the case that these end up showing everywhere. So once we have that, maybe I'll do a couple more examples, introduce this terminology of orthogonal whatever. Then what else? I guess one thing is orthogonal projections. That is very important. Gram-Schmidt has to do with orthogonal projections and so on. Okay, so I'll start with this, okay? A is this, 1, 1, 0, 0. It's a rather straightforward matrix. But I can think of it as a linear transformation from the plane to itself. What I want is this. So relate the column space and null space of A to those of A transpose. Null space and column space of A to those of A transpose. Now, let's remind ourselves what is A transpose. Remember, whenever you take the transpose of a matrix, all you need to do is, you need to replace rows and columns. So the first row of A is 1, 1. That's going to become the first column of A transpose. And the second row of A is 0, 0. That's going to now become the second column of A transpose. Now, in principle, you can think of both A and A transpose to be defined on the same R2, same plane, going into the same plane. But it turns out that it's often better to think of A and A transpose to be working in opposite directions. Okay? If A goes in that direction, A transpose goes in that direction. Part of the reason why is because multiplicativity. Right? So if you have something like this, x, say this is A, this is B, well, B transpose is going to go this way, and A transpose is going to go this way. In other words, remember, when you take the transpose of a product, you don't get to distribute like this. You need to flip the orders. So that's why you want to think of, if A goes this direction, you want to think of A transpose going the other direction. OK. So let's first record null space and column space of A. And while we're doing that, let's also remind ourselves these things. So column space of A, remember, was the span of all columns of A. But that's the definition, or one of the definitions. What are the columns of A? This is just 1, 0, 1, 0. When you're looking at the span, you don't need to just keep repeating the same thing. This is just going to be the span of 1, 0. So if you want to be more explicit, maybe like this. OK? So it's the horizontal axis. That's the column space of A. What was the null space of A? Null space of A by definition is a set of all those vectors x, y, such that A x, y equals 0, or 0, 0. All solutions to A times xy equals 0, 0. Right? When I do this multiplication, in the first row, I get x plus y. In the second row, I get 0. So this just gives me x plus y equals 0. And maybe if I want, I can say y free. OK. If I want, I can think of this as a span as well, just so that they have a basis. So if I were to, for instance, fix y to be, say, 1, then x would be minus 1. And so minus 1, 1 would be a basis vector. But I like x is positive. So let's say x is 1, y is minus 1. OK? I want to do the same thing with A transpose. I can just take it as a 2 by 2 in and of itself. Now, in the textbook, I think, instead of looking at the column space of A transpose, they write row of A, so row space. You can say it that way. I find it more convenient to just keep column space of A transpose. So in the textbook, you'll see this notation. And they will call this the row space, which is the same thing. Span of columns of A transpose. Again, I have two columns, 1, 1, and 0, 0. Remember, this 0, 0 is a 0 vector. It's always redundant. You never need to write it when it comes to spans. So this is just going to be the span of 1, 1. OK, write it here. That's the column space of A transpose. And finally, the null space of A transpose. Again, I need to set up the equation. A transpose times xy equals 0, 0. Maybe I'll use different variables. Let's say u and v. uv equals 0, 0. And so when I do this multiplication, I get u and then v. hang on. I get U0, sorry. So on 0, 0, I want this to hold. This just gives me U. This gives me U as well. So the only solution of this is when U is 0, V arbitrary. I'll erase this. And certainly I can just then say U is 0, V is 1. So null space of A transpose is span of 0, 1. This is old stuff, but I'm just doing a short review. Of course, the matrix could have been much more complicated, in which case these calculations would have been harder, but the idea is going to be just the same. Now, I want to think of R2 to go from here to there, and, A to go from here to there, and A transpose to go from here to there. I'll draw it over here. Okay. Okay. This is my A. It's a transformation. Now I'll add the column spaces and null spaces. Okay, in fact, I'll use orange here and green. So first I want to draw the column space of A. This one, orange. That's certainly the horizontal axis in the output space. Okay, that's the column space of A. What is the null space of A? Okay. It's the span of 1 minus 1, so it's the second diagonal if you want. But instead of drawing null space in the output space, as usual, I'm going to draw it in the input space for A. So this is the null space of A. Okay. And like I told you, for A transpose, I'm going to switch the rows of input and output spaces here. And I'm going to think of A transpose to be going the other direction. Now, this is not to say that A transpose is the inverse of A. Indeed, when you just look at the determinant, you're going to realize that this guy is not invertible. I'm not saying A transpose is the inverse. Okay, I'm not saying that. I'm just saying it goes backwards. So if I were to look at the column space of A transpose, it's this guy, 1, 1. And you're going to get this first diagonal. Column space of A transpose. You see? This is a span of 1 minus 1. That was the null space of A. On the other hand, the span of 1, 1 was the column space of A transpose. Now, if I were to dot this vector and this vector, I'm going to get 0. Okay, let's do it over here. Take this, dot it, inner product it against this guy. And I can write it like so. How did we do this? Well, this is nothing but take the left matrix or vector, transpose it, then multiply. 1 minus 1 transpose 1, 1. This just corresponds to multiplying the corresponding entries and then adding everything up. So 1 times 1 is 1, plus minus 1 times 1 is minus 1, so it gets 0. So you see, this guy is perpendicular to this, which means the null space of A is perpendicular to the column space of A transpose. I can safely put here 90 degrees and write, I'll write it here. Right, so this is perpendicular to this. In other words, the orthogonal complement of this is the same thing as this. Take the null space of A, look at the orthogonal complement. That's the same thing as the column space of A transpose. Okay? How I keep this in mind is this. If I look at the null space of a transformation and then take the perp, I get to put the perp inside, but you flip it. Okay? Upside down T becomes like this, and you flip null to col, and vice versa. Pretty nice. Let's do it here too. I forgot to draw this. Null space of A transpose is the vertical axis. Okay. So that's the null space of A transpose. And again, by the same reasoning, we had done this before, but let's do it again. If I dot this against this, I'm going to get 0, which means that 1, 0 is perpendicular to 0, 1. Standard basis vectors are perpendicular always. Okay, so I can put here perp. And what do I say? Column space of A transpose is null, column space of A perp is null space of A transpose. Okay. So whenever you're looking at column space or null space of a transformation, and whenever you're taking the perp of it, you get to put the perp inside the parentheses, but you just cannot just look at perpendicular of a transformation. You sort of turn it into a transpose, and you flip column space into a null space, and vice versa. Okay? Any comments or questions about this? Ultimately, this is the second version I want to state for the fundamental theorem of linear algebra. Okay. I'll write it here. This works more generally. So, fundamental theorem of linear algebra, version 2. Let A be m by n. So I'm thinking of A going from Rn to Rm. Okay. And consequently, A transpose goes from Rm to Rn. Okay. Then, well, I'll store the rank of A in a variable as well. Put R to be the rank, R number of A. Then there are multiple ways of writing this. Let's first remind ourselves the original versions. Right, so if I were to apply the fundamental theorem of linear algebra to A, that would give me that n equals rank plus nullity of A. Or maybe I'll just write it like this. Nullity of A is nothing but n minus r. Okay. If I were to look at the rank of A transpose, that is in fact the same thing as R. I'm not sure if we discussed this before, but when you take the transpose of a matrix, our number doesn't change. Kind of surprising, at first at least. And consequently, if I were to apply the fundamental theorem to A transpose, I would get that the nullity of A transpose is M minus R. So these are the dimension counts. But furthermore, I'll write it here too. Basically, I'm going to try to write this out. So what do I have here? I have the null space of A and the column space of A transpose. I want to say these are perps of each other. Okay. This. And of course, if I started with this and take the perp, I'm going to get back this. I'll write it as well. That's also somehow useful. Okay. Then I can look at these two guys. Column space of A perp is the same thing as the null space of A transpose. Or I can just take this and take the perp of this, and I'm going to get back to column space of A. Okay. That's the second version of the fundamental theorem of linear algebra. I often find it a lot more useful to draw the picture like this. Even though in general, M and N could be like arbitrary, just draw the sort of two-dimensional picture as a schematic to remember what is what. I'll do one final thing here, just to reorient ourselves. Some of these spaces over there are subspaces of Rn. Some of them are subspaces of Rm. I'll delete the picture. Let's try to guess or figure out where we should be putting these 8 subspaces in a sense. Okay. So now I ask you, is the column space of A a subspace of Rn or Rm, given that A is m by n? A is m by n. I'm asking, column space of A is supposed to be a subspace of something, but is it a subspace of Rn, or is it a subspace of Rm?
Column space is always going to be a subspace of your output dimension, so this would be n. Rm for the column space.
Okay. How about the null space of A? Someone else. Where is the null space of A?
Using that same logic, it'd be in R of n because it's a subspace of the input space.
Very good. Where is the column space of A transpose? Someone else.
Rn.
Very Good. Null space of A transpose. Someone else. Say again? Yeah. Okay, we have these. Now, whenever you have a vector space like this and a subspace to it, when you take the perp of it, that's sort of like a general rule, the perp of it, the orthogonal complement, is going to be yet another subspace of the same space. So if you start with the null space of A, don't care. If you were to start with a subspace of Rn, take the perp of it, the perp is going to be still a subspace of the same space. Okay? So, null space of a perp is again going to be a subspace of Rn, and the perp of this is going to be again a subspace here. You're not going elsewhere. Okay? And likewise here, if I start with the column space of A, take the perp, you're going to stay again as a subspace of Rm. And again, if I were to look at the null space of A transpose, and then take the perp, you're again there. By the way, for the null space of A transpose, you might see the word left null space of A in the literature. This is also called the left null space. I think it's also called the coimage of A, but that's sort of fancier language. Let's not get into that. So the fundamental theorem of linear algebra relates these 8 subspaces, okay? This cannot be the same thing as this in general. So this should be the same thing as this. And these two should be the same. Okay? And here too, this probably is not the same thing as this, so it should be this. Okay? These are the same spaces, the subspaces that I connected with arrows. Finally, in terms of dimensions, remember I said rank of A is R. So column space of A is R-dimensional. This guy is the same thing as this. This is also R-dimensional. Whenever you have a subspace, well, the dimension of its perp is going to be M minus R. So let me remind you this. This was a rule that I mentioned last week. If you have a subspace W of V, then dim of W plus dim of W perp is going to be dim of V. So the dim of Rm is M, of course. Maybe I'll write it as well. And the dimension of this and the dimension of this should add up to M, which means the dimension of this should be M minus R. And this, again, are perps, which means that the dimension of this is M minus R, which is the same thing. I mean, you can also think of it as saying that these two are the same. See, their dimensions are the same. And likewise here, dimension here is N. Column space of A transpose, I told you, is the same dimension as column space of A. This is R. This is its perp, dimension N minus R. This is the same thing as this, dimension N minus R. This is the same thing as this, dimension R. Okay. I just rewrote this fundamental theorem of linear algebra, again using these sort of like a chart. So if you try to use it initially with dimension counts, whatever, you might get confused. I would recommend that you draw the picture. Just draw sort of like a simple picture like this. Draw something like this. Okay. Say this is the column space of A. I like to put verticals as the null spaces and column spaces as the horizontals for whatever reason. Null space of A transpose goes this way, so this should be the column space of A transpose. This should be the null space of A transpose. And the picture tells you that these two are perp and these two are perp. That's a better way of remembering it. But then again, some people like this algebraic approach more. I get confused with the algebra. Okay? Pretty useful. After we discuss singular value decomposition, we're going to discuss that in a couple of weeks. We're going to restate the fundamental theorem once more in terms of singular values and stuff. So everything is going to come together in a really nice fashion. Comments or questions about this? Okay. Now, I want to introduce some terminology. Within this business of orthogonality, you call sort of different objects always orthogonal for whatever reason. I found that very confusing when I was first learning it, but it ends up being useful to some extent. You sort of fast forward a bunch of things. I think I'll write it here. I want to define orthogonal sets or bases, orthonormal sets or bases, an orthogonal matrix or a transformation, and an orthogonal projection. This orthogonal projection is going to take more time for us, but the remainder I'm just going to state. Let V be an inner product space This just means V is a vector space and you have an inner product specified on it. In principle, this is just, Rn with the standard dot product, but it works more generally. An orthogonal set of vectors, or orthogonal basis, so a set of vectors, a set S of vectors in V is orthogonal set if given any two vectors that are distinct, they are orthogonal to each other. If for any, say, S1, S2, and S, if these are distinct vectors, then they are perpendicular. So I can just write it either way. Orthogonal basis is defined the same way. The basis where any two distinct vectors are orthogonal. Orthonormal is, in addition, you have that each vector is normalized. A set of vectors. A set S of vectors in S is orthonormal, not orthogonal, orthonormal, if it is orthogonal and each vector is unit. each vector S in capital S is unit. Remember, unit means it has norm 1. And likewise, the same thing applies for an orthonormal basis. The common abbreviation for this orthonormal basis is ONB. It's very common. ONB. Okay. This Gram-Schmidt algorithm that we're going to discuss probably starting from tomorrow is an algorithm that starts with any basis and transforms it into an orthonormal basis or an orthogonal basis, depending on how you sort of cash out the algorithm. But typically people go for ONBs. Okay. Well, we'll get there later. I want to define one more thing. Orthogonal matrix or transformation. Let say U be a linear operator or matrix, square matrix. I'll write it like that. Then I'm going to say U is orthogonal if U transpose equals identity and U transpose U is identity also. Okay. So in a sense, orthogonal transformations are very useful as well. There's a bunch of different properties. Maybe I'll leave it as an exercise. I'll just leave it as a theorem, perhaps. Maybe this is too hard for an exercise. I believe this is in the textbook. U is orthogonal if and only if its columns form an orthonormal basis. Which is kind of confusing. You don't call U orthonormal matrix, you call it orthogonal matrix. But its columns are orthonormal. It's tradition at this point. What else? Well, it in fact preserves inner products, norms, whatever. Distance preserving, so isometry or angle preserving. Or inner product preserving. So pretty useful. I would rather give examples. Let's start with orthogonal matrices. The other ones are not, we'll get there later. So first of all, for instance, any permutation is orthogonal. Okay? So example. Well, in Rn, standard basis is orthonormal. Each of them have length 1. They are certainly perpendicular to each other. So standard basis is O and B. But then, if you were to look at a permutation matrix, each of its columns is going to be one of these, but perhaps in a different order. By this idea, then any permutation is orthogonal permutation. Okay. So in a sense, orthogonal matrices are generalizations of row interchanges, if you want. You can also think of orthogonal matrices as generalizations of rotations. Rotations are orthogonal also. Let's do this, for instance. Remember, r theta was this rotation by theta degrees in the counterclockwise direction. Right, so the rule for it was cosine of theta minus sine of theta, sine of theta, cosine of theta. You can just dot this with this, right? So this is minus cosine times sine. This is plus cosine times sine. So certainly the columns are orthogonal. Cosine squared plus sine squared is 1 by trig, and these are unit as well. You can think of, so you can just use this idea that columns of this rotation is an orthonormal basis. Or you can directly compute r theta times r theta transpose. Let's do that. Right. That's my r theta. And then I'm going to have cosine minus sine, sine, cosine. And in fact, I'll write this as well, like that, to abbreviate. C minus S, S, C, C, S minus S, C. Okay. C squared plus S squared is 1. CS minus SC is 0. CS minus SC is 0. S squared plus C squared is 1. Okay? So these are orthogonal. A wonderful property is that orthogonal matrices, just like permutations or shears or lower triangulars or diagonals, whatever, they are closed under multiplication. In other words, they form a matrix group. You can group orthogonals together. example, UV orthogonal means U times V also orthogonal. You can do it in a bunch of different ways. I like just using this expression, right? So you can just take UV, multiply it against UV transpose. When you take the transpose of a product, you need to flip the orders to distribute. But since V is orthogonal, this is identity. Drop it. Like this. This is also identity, so everything is identity. That's how we can show this. So you can just group orthogonal matrices together. In particular, for instance, in 3 dimensions, what you can do is you can compose rotations in different directions to come up with an orthogonal transformation in 3D. So for instance, what I can do is I can rotate, say, around the z-axis and then around the y-axis, say. So for instance, I can look at this. This rotates by theta degrees along the z-axis. Then let's say I'll do it here. 1 r times, so r sub psi. This rotates along the x-axis by psi degrees. Okay. So the composite of this is going to rotate first by theta in the z direction, and then again like this, by psi in the x direction. The composite of this is again orthogonal. Okay. The picture is perhaps kind of confusing. Just imagine what this is doing. This fixes the z-axis, rotates the xy. This fixes the x-axis, rotates the yz. When you multiply, orthogonal times orthogonal is orthogonal. So this whole thing is going to be a 3-dimensional orthogonal transformation. Okay? I think it's time for us to stop for today. We're going to continue tomorrow with orthogonal projections. Thank you. All right, let's start. Good morning. Today we're going to start talking about orthogonal projections. This is one of the most important ideas. We're going to keep using orthogonal projections throughout for the rest of the course. I'll say this, okay? An orthogonal projection in an inner product space. So orthogonal projection is going to be a linear transformation from V to itself, so a square matrix, that has the specific property that the transformation squared is the same thing as transformation done once. Okay? Proj of V is a linear op T such that T times T equals T, or such that T squared is T. Okay. This is the fastest way of defining orthogonal projections, but perhaps not the nicest one to use, geometrically say. But this equation t squared equals t, we in fact we encountered a couple times already. So for instance, in one of the previous problem sets, we had this linear transformation acting on square matrices that symmetrized the matrix. If you feed to this curly S a square matrix, this symmetrization, you've calculated that applying symmetrization twice is the same thing as applying it once. So somehow this, I'm saying, is an orthogonal projection. With respect to which inner product, it's not super clear, but you see it's rather useful to think about this idempotence relationship. The rest of this class today, I want to sort of relate this back to inner products in the case of Euclidean spaces, or Rn. Another name for this orthogonal projection is projector. We can also call it a projector. Okay. Now here's sort of a complementary way of thinking about orthogonal projections. Well, any linear transformation, well, you can associate any linear transformation to subspaces. One of them is the column space, the other one is the null space, or image and kernel. And if you want to sort of understand orthogonal projections from the perspective of geometry, you really focus on the image of the supposed orthogonal projection. Okay? And so first, we're going to start with Rn, and we're going to take a, say, line, that is to say the span of one vector, and we're going to try to orthogonally project whatever vector onto this vector that we started with. So here's, for instance, one example. I'm in 2 dimensions, y onto u. Okay, so let's say here's my one vector for 2, and another one is 7, 6. What I want to do is I want to project y onto the span of u in an orthogonal fashion. So I'll write it. Project y onto u, onto the span of u, maybe. Okay, I'm going to write this vector as proj sub u of y. That's sort of the notation they use. And they call it y hat in the text, even though this notation is not very universal. So that's going to be another vector. Let's try to figure out what this should mean. I'm not going to draw the coordinate axis. I'm just going to draw the origin, like this. Here's my u, and here is some other vector. Is y. When I look at these two, I realize these are not proportional. So indeed, y is not going to be in the span of u. So the picture is like this, and they have some angle between them. Let's call it theta. When I look at the span of u, I get the whole line spanned by u. Okay, that's the span of u. In this picture, y hat is going to be this orthogonal projection of this vector onto this. Well, you draw this line. This is going to be the orthogonal projection of y onto the span of u, or onto u. Okay. So y hat, in this case, is going to be a vector that is in the same direction of u. It's in the span of u. But its magnitude is so that this geometric picture is correct. Now, we need to do some sort of a calculus or some sort of geometry. I know, for instance, that if I were to look at this right-angled triangle, the length of this side, the hypotenuse, is nothing but y norm. Okay. And since this is theta, I'll write that as well. So the angle, I'm saying, between u and y is theta. Well, y hat, then the formula of y hat should be u scaled by an appropriate length. And that length should be, well, cosine of theta times magnitude of y. So this length, magnitude of the projection, should be y hat, or sorry, y norm times cosine of theta. Okay. So what I can do is this. I can start with u, normalize it by scaling it by its norm, then renormalize it using this magnitude. Okay. So I'm just first deriving the formula, and this is also something you can use in case you forget. You can just draw the picture and try to remember things. Okay. Start with the vector u. Scale it. Now you have a unit vector. Rescale it using this scalar. All right, better. Okay, that's the formula. So I'll write the types of these things here. U is a vector, okay. All this stuff, just a bunch of scalars. Okay, so I'm saying y hat, the orthogonal projection of y onto u, is u up to some scalar. That's what it means for y hat to be in the span of u anyway. But of course, the point is, we need to somehow recalculate this business to come up with a nicer formula. So you can do it like so. Remember, we had this rule. If you have two vectors p and q, its inner product, or their inner product, is p norm, q norm, cosine of the angle between. Okay? And so in this case then, y norm times cosine is inner product of u and v divided by the norm of u. Oh, I'll write it here. This is, right, so I'm just going to solve for this part, say. Y against u divided by norm of u. I have another factor here times u. But then in the denominator, I have norm of u squared. That's the same thing as u against u. So I can just write it like so. That's the formula. Take your y, hit it against u, that gives you one number. Divide it by u against u, that's another number. That's a scalar now. Use that scalar to scale u, and that gives you y hat. So this is what I need to compute. I need to compute a bunch of different things. Instead of sort of starting like this, I would suggest compute the numerator separately, denominator separately, whatever, and then put everything back together. And so y against u, first we need to compute. So 7, 6 against 4, 2. Okay, this by this is 28. This by this is 12. And so you have 30, 40. That goes in the numerator. In the denominator, I'm going to have u against u. So 4, 2 against 4, 2. 16 plus 4 is 20. All right, like this. 16 plus 4 is 20. So in the denominator, I should be putting 20. So this is going to be twice u. Two times, so 40 divided by 20 for 2 is 8, 4. Okay. Just checked that I was doing everything correct. That's the orthogonal projection of y onto the span of u. Now, in this picture, I drew it so that y hat is, it looks like it is smaller than u, but clearly it's larger. So I should have drawn it differently. So this is sort of like a schematic. Okay. Questions or comments about this? And you see here, in this formula, right, I'm fixing u, and for fixed u, this expression is linear in y. Because once you fix u, this is a fixed scalar, fixed vector, and dot products are linear. So it's a linear transformation, as you see. And furthermore, if I were to apply the same thing twice, so if I were to look at the proj sub u of proj sub u, I'm going to get back the same thing. Let's do that too, just to verify that indeed this idempotence relationship is verified. So the complication in this orthogonality theory is, well, you have a bunch of scalars and stuff, but of course you can put the scalars inside the inner products because they are scalars after all. So it might make things slightly complicated. So if I were to take that vector I ended up with and apply the same thing, I'm going to get the same vector. So this is what I want to compute. The inner one is, we computed it to be 8, 4. Okay, I'll do this once sort of in the long way. At this point, what you can do is you can, for instance, pull out the constant because it's a linear transformation, but never mind. I said that you forgot all that. I'm just going to compute this against this. What was it? 4, 2 divided by 4, 2 against 4, 2. This scalar I'm going to use to scale 4, 2. Okay. At this point, what we can do is we can take out a factor of 2 from this inner product, and the numerator and the denominator would cancel, for instance, and you would again get back 8, 4. So you see this proj sub u is something that once you apply it once, well, you don't need to apply it again. which kind of makes sense because once you orthogonally project something onto something else, well, if you project it again onto the same thing, you're not going to move. Okay. Any comments or questions about this? Now, the order here matters. So projecting y onto u is not the same thing as projecting u onto y. Okay, let's compute that as well. Going to keep the formula. So this was what we had obtained before. It's going to be very similar, as you see, but if I proj y onto u, I get something proportional to u. On the other hand, if I were to do it the other way around, if I were to proj u onto y, I would get something proportional to y. Oh, y, parts of y of u. And of course, if you look at the formula here is not linear in u. You're multiplying u against itself and whatever. Certainly not linear. It is quadratic, though, degree 2. Okay, so let's compute this also. I'm just going to use the formula. Proj sub y of u. Okay, u against y against, or divided by y against y times y. Now, the numerator we had computed, right? I forgot, but let's compute it again, I guess. So it's 4.2 against 7.6. That gave us 40. The denominator we hadn't computed before. I need to look at y against itself, 7.6. That's 49 plus 36. That gives you 70, 85. Okay, so plug in the numbers. (40 divided by 85 times 7.6). Yes, if you want, you can factorize a little bit. Divide by 5 gives you 8. Divide by 5 gives you 17, I think. And then you can't go any further. If you want, you can distribute the scalar over there, but that's a perfectly nice answer. Okay. Any comments or questions? Here's a nice relationship between this proj and perp. Remember, given any subspace, we could look at the set of all those vectors that are orthogonal to any vector in the subspace you started with. So if I have, for instance, here u, okay, I can look at its perp. Okay, it's going to be this line, some line that is perpendicular to it. Why is it a line? Because in this case, we're in 2 dimensions, and the dimension of the subspace plus the dimension of its perp add up to the total dimension. So u perp is going to be this, But this is also precisely the kernel of projection onto U. In other words, if I have some vector z such that when projected onto U gives you the 0 vector, that's the same thing as saying that z is orthogonal to U. Let's do that here. If z is a 2D vector such that when projected onto U gives you the 0 vector, so 0, 0. Oh, I can write it like this. Z is a vector like this if and only if z is perpendicular to U. That's what I meant. Well, why is that the case? Because we know, by definition, z being perp to U is the same thing as saying that z against U is 0. Right? So this is the same thing as saying that z against U is 0. But then if you look at the formula for proj sub U, in the numerator you're going to have this expression. So the only way this proj is going to be 0 is if this scalar in the numerator is 0. Right? So z being perp to U is the same thing as saying that this numerator in the scalar part is 0. Okay. And here's a nice idea here as well. If that is the case, I'll go back to this picture. Here's the origin. Here is U. Here is its perpendicular. Oh. Here is Y. Well, of course, I can project Y onto U and U perp. These are going to give me two different vectors, but they're going to be, components of Y. So I can do this, or I can do this. In physics, perhaps you've seen sort of splitting forces into different directions, whatever. It's the same idea. So Y equals proj sub U, or maybe, yeah, sub U of Y plus proj sub U perp of Y. Okay. This is the main idea with orthogonal projections. The complication is, well, when you try to project onto a higher dimensional subspace. You should be able to still do that also. Certainly imagine, for instance, you have a three-dimensional vector. Say you're trying to project it onto the xy plane, or whatever plane you want. So there's a similar thing, okay? The idea is pretty much the same, except the formula is more complicated, okay? You are responsible for the formula, so we're going to study it. But before that, are there any questions? Okay. So now I'll take some other example here. Maybe even before that, I'll say one thing that kind of hints at the general formula. Okay. So this is the formula of orthogonal projecting, or orthogonally projecting any vector y onto U. But I can try to think of it as some sort of a matrix product as well. Okay, that's what we need to do. Now, don't worry about this, the denominator. Set that aside. The really important part is y against u is an inner product and then multiplied by u. That I want to sort of make sense of. And you can do this for that. I think I'll erase this. Okay. This is by definition y against u divided by u against u times u. Okay. Set this number in the denominator aside. So I'm going to write it like so. Okay. This is going to be somewhat confusing. Now, what are the types of these three things? That's a scalar. Don't worry about it for now. This is also a scalar. And this is a vector. And this is a scalar product, or scalar multiplication. Vectors being n by 1, okay, n rows, one column, right? It's a column vector. I can think of it as a linear transformation from R1 to Rn. Okay. So thinking of U as a linear transformation from R1 to Rn, I can change the orders of these. After all, this is a scalar. In other words, it's a one-dimensional vector. Okay? And so I can say this scalar vector product is the same thing as this vector acting on this one-dimensional vector. So I can reorder these. U like this. And in fact, I'll write U first as well here. But then I know what this is. This is U transpose times Y. Okay. So get rid of the Y. I'm just telling you that orthogonal projection onto U is the same thing as this exterior, or what was it, outer product. This was something that we defined like 5 years ago or something. But you see, you can think of proj sub U as this linear transformation also. And this is sort of the hint that tells you what should happen in the general case also. I'll write it here. You need to start with a non-zero vector. Rn to Rn, right? That's a linear transformation. The first formula is this: y against u divided by u against u times u. Or you can think of it as that matrix product. I'll write it like this: 1 over u norm squared u transpose times v times y. In other words, proj sub u is literally this n by n. Okay. In particular, it's clearly a linear transformation, it being the composite of linears. Okay. So for instance, in this example, it tells you that you don't need to worry about y at all if you just compute that thing, this thing over here. It's going to be a 2 by 2 matrix, it being an outer product, and it is going to be exactly the projection transformation. So I'll write it here. So in our example, u was 4, 2, and y was 7, 6 in R2. According to that red formula, this projection operator associated to u is 1 over u norm squared. U norm squared was 16 plus 4 is 20. 1 over 20 times u transpose. Okay, 1 over 20 times 4, 2 against 4, 2. Like this. Okay, projections are going to be linear transformations. So this is going to be a square matrix. Okay, it's not a number. This is not an inner product. It's an outer product. So when you do this multiplication, you get this 16, 8, 8, 4. If you want, you can distribute everything. Let's see, I can divide by 4 everything. 4 over 5, yeah, 2 over 5, 2 over 5, and then 1 over 5. Okay, pretty nice. So if I were to take this, left multiply it by this, or right multiply it by this, I should get back the original two-dimensional vector we computed. So let's do it. All right, so 4 over 5, 2 over 5, 2 over 5, 1 over 5. This times 7, 6. 6, 7. 28 plus 12, 40 divided by 4, 40 divided by 5 here. 14 plus 6, 20 divided by 5. As you see, we again get 8, 4. The benefit of this formula, of course, is that now you have an expression for proj sub u itself, so you can just plug in whatever vector y you want. You can do the same thing over here too, but it's going to be slightly nastier, the expression. Okay. Any comments or questions about this? So you see, somehow orthogonal projections have to do with inner products, but they also have to do with outer products. Okay? So, okay, I'll leave it there for now. Somehow, if we try to take a vector and orthogonally project it onto some subspace of higher dimension, we're going to have an expression of a similar type. Or we're going to have sort of a linear combo of things like this. Okay. Any comments or questions before I move ahead? Okay, so here's the next example. Now I'm going to look at 3 dimensions, and I'm going to look at orthogonally projecting one vector onto a 2-dimensional subspace. This is the rule for 1 dimension, or rather, projecting onto a 1-dimensional subspace. I'll mention one thing too. If the vector you started with that you're trying to project onto was unit to begin with, it was normalized, well, that would mean that this denominator is 1, so you would not need to write it out. Okay? Orthogonally projecting onto a unit vector would be just take your vector you're trying to project, hit it against the vector you're trying to project onto, and use that scalar to scale your unit vector. It would be much simpler. Okay. So here's the example. Now we're in 3 dimensions. The notation in the textbook is somewhat throwing me off. I'll say this, okay? In the literature, often people use U and V and stuff for unit vectors. In this case, this is not units, even though in the textbook they use this letter. So I'm just letting you know. Often, when people use U, that means it's a unit vector. But we're just sticking to the notation in the textbook. Say you have this vector, and then this other vector. Okay, and then I have a third vector like so. Y is 1, 2, 3. These are vectors in R3. Now, I'll look at the span of U1 and U2. Let's call it W. Okay. Can I say immediately that this W is 2-dimensional? No, maybe not. Who thinks that they would need to calculate a little bit? Some people, okay. So here's a shortcut. If you're trying to figure out if 2 vectors are linearly independent on that, you can just eyeball if one of them is proportional to the other one. Okay, so I look at, for instance, the first entries. Okay, so this is -1 times this, but then the second entry is not -1 times 5. So these two are not proportional, therefore they must be linearly independent. Okay, that's a shortcut. It's a very useful shortcut. Which means this is a 2-dimensional subspace in R3. I'll write it. You can also, calculate whatever, set up the equation, but it's better to just eyeball at this point, if you can. Okay. What I want to do is, I want to project Y onto W. What is orthogonal projection of Y onto W? I'll mention maybe later, maybe tomorrow, a more sort of calculus-like characterization of orthogonal projections also, but for now let's just try to stick to geometry and linear algebra. So I'm just going to draw a schematic. Here's my W. It's a plane. Okay. Here's the origin. Here's Y. When I do this orthogonal projection, again, let's call it Y hat. Well, I should get this, right? y hat should be some vector in the span of u1 and u2. Okay. I need to be able to calculate this. Well, I'll try to draw a bit different picture. Let's do this first. In this case, things are slightly easier, I think. Yes, because we're in a nice situation where u1 and u2 are perpendicular to each other. Okay, that's very nice. So u1 against u2 is 2, 5, minus 1, minus 2, 1, 1. Right? So that's minus 4 plus 5 minus 1, that's 0. So these two vectors, the vectors that span W, are perpendicular. They're not unit vectors, but okay. At least they are orthogonal. And so remember, in this situation, we can say that u1, u2 is an orthogonal basis for W. I'll write that too. When you have a basis of your subspace made up of pairwise orthogonal vectors, you call that basis orthogonal basis. Is an orthogonal basis of the subspace W. Whenever you have an orthogonal basis of your subspace you're trying to project onto, things are fairly nice, okay? Because of this. This is what we're trying to calculate. I'll draw the picture again, like so. That's my W. Here is the origin. Here's my basis vectors. Here's, let's say, u1, here's u2. And the angle here is 90. I took some other vector. It's not in a span, even though it doesn't really matter. This vector, we can just take it to be not in the span of u1 and u2. So this y vector just sticks out. Okay. When we project it, All right, let's start. Apologies for starting a little late. I thought it would be good to double clean the board. So we were talking about orthogonal projections. We were working on an example. I'm going to get to that. We're not done with it. I want to finish calculating it. And then we're going to transition to the Gram-Schmidt algorithm. But just to remind you, we were looking into this orthogonal projection business, right? These formulas work whenever you have an inner product space, really. So a vector space together with an inner product satisfying certain axioms, whatever. But of course, the first example is for us to understand Rn with the standard dot product. Well, I told you just to connect it to this abstract perspective for projections. If I have a V inner product space, a transformation P from V to itself, I'm going to call, remember, a projection or orthogonal projection. If applying it twice is the same thing as applying it once. Okay, it's idempotence relationship. This was sort of the abstract perspective. I like this because it's rather fast to say it. P squared equals P. It's a nice algebraic expression. But in practice, we often take V to be Rn, and we try to orthogonally project onto a subspace in it. Right? So I want to connect this perspective to the subspace perspective. Well, what you can do is you can look at the image and kernel of this transformation. Remember, image is pretty much the same thing as column space. Kernel is pretty much the same thing as null space. And image of P and kernel of P are subspaces of V. Yes. Well, the picture is something like this. Okay. I'm just going to pretend that these are like two-dimensional or one-dimensional, whatever. But the point of looking at P always is something like this. If I were to take an arbitrary vector y, well, I can project it onto image. When you projected something into something, P of y is going to be, by definition, in the image. But also, I have this other component. And certainly, kernel of P should be orthogonal to image of P. Okay. This you can deduce merely from this algebraic expression, algebraic equation. Another thing you can do is you can look at identity transformation minus P. If you were to square it, meaning if you were to apply this transformation twice, identity minus P itself is a linear transformation from V to itself. Well, you just expand it like this. Okay, expand further. This is I minus P plus P squared. But insofar as P squared equals P, say these two cancel out. And so I minus P2 satisfies the idempotence relationship. And certainly, I minus P takes a y and projects it onto the kernel of P. So this would be I minus P applied to y. And consequently, kernel of P would be the same thing as the image of I minus P. And image of P would be the same thing as kernel of I minus P. So you see, just starting with this P squared equals P equation, you can get a lot of things. So this, because of this, this equation is very important, idempotence equation. Maybe I'll leave it as an exercise. In any sort of inner product space like this, let's say finite dimensional for technical purposes, because otherwise I need to assume something more. Assuming that V is finite dimensional, if I were to take any subspace of V, then in fact there's a unique orthogonal projection P, whose image is that subspace you chose, whose kernel is the perpendicular orthogonal complement to it. This is a slightly hard, perhaps, exercise. I guess all of those over there are also exercises ultimately. Given any subspace W of V, there is a unique P such that P squared equals P, image of P equals W. And consequently, the kernel is W perp. So you can, in fact, think about subspaces of any space, or alternatively, you can think about the space of orthogonal projections. Pretty nice. Turns out that it becomes important to be able to think about subspaces of a space itself. This is sometimes what is called the Grassmannian of V. For instance, an early attempt in trying to formalize, as far as I understand, logic of quantum systems, von Neumann and another major mathematician, or son of a major mathematician to say the least, Birkhoff, modeled events for quantum systems as subspaces of some inner product space. Pretty cool idea. And so in order to model a logic, you need to be able to say, oh, if one subspace corresponds to one event and another subspace corresponds to some other event, then there should be some other subspace that corresponds to both of them happening, or at least one of them happening, or you need to come up with something about complementation also. So in their model, for instance, taking the perp operation of a subspace correspond to the logical operation of saying not for whatever event. Okay, pretty interesting. And maybe, if time permits, later on we'll sort of discuss it a little bit more, how to sort of model some version of quantum logic based on subspaces. At this point, it's not very important for us, of course. But, you know, we can sort of take these ideas and sort of kind of run with them and reach to great heights. So from a more applicable purpose, from the more practical point of view, in the case of Rn, we had, if we have a non-zero vector, we talked about how to orthogonally project onto the span of U, proj sub U, right? This is a linear transformation from Rn to Rn. Proj of proj is again proj, so it is a projection. What was the formula? The formula for orthogonal projecting onto the span of U was, well, you feed to it a y, and then, well, you dot it against U, that gives you a scalar, divide that scalar by U norm squared, okay, and then use that scalar to scale the vector U. So maybe I should write it somewhere else, and with a different color also. So I'll write it here. For U non-zero, orthogonal projection onto U, or the span of U, is proj sub U, using the notation in the textbook. So you feed to it a vector, and you look at this guy. Y against U, that's a number, divided by U against U, that's another number. Use this number to scale the vector you're projecting onto, which is U. We also realized you can think of it as an exterior or outer product, like so. And in principle, since 1 over U norm squared is a scalar, I can distribute this inside too. I can think of it like this also. Okay. So ultimately then, I can simply say proj sub U is this n by n. Okay. That's a situation when you're trying to orthogonally project onto a one-dimensional subspace, the span of one vector. But the example we were looking into was, well, we were looking into the three-dimensional space, and we were trying to orthogonally project onto a two-dimensional subspace. Let me remind you where we were. That's the example. I think I'm going to... Oh, this one doesn't have the thing. Okay. I'll erase this. Maybe I should start wiping like the Europeans do. If you ever watch a lecture from an institution in Europe on YouTube, you're going to see it's like there's like a bucket of water. And it's like when they're done with what they're writing, they just like take a wiper and they actually like wipe the whole thing, dry it and stuff. Because Europeans are not about efficiency. It was so funny. A couple of years ago, I was in France for a while, and they gave me an office there. And funny thing, okay, they closed the department at like 5 p.m. Like you have to leave, which is like very counterintuitive from an American point of view. What do you mean I don't get to stay here until 2 a.m.? If it's too hot, they just like don't work. So, okay. So this was the example. We're in 3 dimensions. 2, 5, minus 1 is the first vector. U2 is minus 2, 1, 1. And then y is 1, 2, 3. Oh, 1, 2, 3. The point was, we looked at the span of these two vectors. That's a 2D subspace, because these are linearly independent. These are not proportional. Whenever you have two vectors that are not proportional, that means they're linearly independent. So this is a two-dimensional space. I'll write it. And consequently, this is also a basis for W. What else did we see? Well, one thing we computed was, well, I'll mention it in a second, but what I was trying to compute was, I was trying to compute the orthogonal projection of y onto W. Okay, so things are slightly more complicated this time. But the nice thing about this example is when you dot this against this, we get 0. That is to say, u1 and u2 are orthogonal. So I'll say this. Whenever you see something like this with orthogonal projections, whatever, right from the get-go, I would suggest just compute all dot products. Ultimately, you're going to need it. Okay? So you just compute everything. What else? u1 against u1, u2 against u2. If you want, you can compute y against y as well, but that we're not going to use actually. So these we want. Let's compute. I think I can just fast forward at this stage. -4 plus 5 minus 1 is 0. Right, so this gives me that u1 is orthogonal to u2, and consequently, u1, u2 is an orthogonal basis for W. Basis for W. Now I need to compute this against this. 2 plus 10 is 12. Minus 3 is 9. This against this, minus 2. Now it's 0. Now it's 3. u1 against u1, 4 plus 25 plus 1, 30. 4 plus 1 is 5, plus 1 is 6. So whenever you have a problem about orthogonal projections and stuff, you're going to need all these inner products. I would suggest just compute them on the side right from the get-go. You're going to need these scalars. These scalars are important. OK, now what was the idea? The idea is this. Here's a schematic. OK, this is my W inside 3 dimensions. Somewhere here is y, and I know that u1 and u2 are vectors in W that are orthogonal. When you're trying to draw these schematic pictures, I would suggest instead of trying to be accurate relative to the xyz coordinates, just draw your subspace to be horizontal, and sort of, if you have perpendicular vectors like this, just think of them as x and y. So this caricature is going to help you sort of orient yourself. This is u1, this is u2. And when I project, I get this proj sub w of y, which again, I think in the textbook they also use the notation y hat. It's not very common, but some people do use it. So like this. This guy is going to be y hat, which is the same thing as proj sub w of y. What was the big idea? Well, and this is 90 degrees again. Instead of directly projecting onto W, what you can do is you can take this W, project it onto the span of u1. That gives you the u1 coordinate of y hat. And likewise, project the y onto u2. That gives you the u2 coordinate of y hat, and then add these up. OK? And so all I need to do to compute this then is, well, project onto u1, add to it the projection onto U2. Okay? Now, expand these using the formula. Let's leave this to the side for now. Let's use this just for a moment. Okay, like so. Now I need to plug in the scalars and the vectors in the right places. So this is 9 over 30 times U1, 2, 5 minus 1, plus 3 over 6 times U2 is minus 2, 1, 1. I guess there are some cancellations. Let's just try to simplify this just a little bit. Divide that scalar by 3 to get 3 over 10, 2, 5 minus 1, plus, of course, this is 1 over 2, minus 2, 1, 1. And you see this is already in the span of W. You can sort of always check that you're in the right track. Because you see this is a linear combination of U1 and U2, so we can keep going. Consolidating these terms, I have 6 over 10, or before consolidating, probably it's better to turn this 1 over 2 into a 5 over 10. Okay, now things are going to get nicer. So 6 minus 10 is minus 4 over 10. 15 plus 5 is 20 over 10, so that's 2. Minus 3 plus 5 is 2 over 10. That's 2 over 10. So I can maybe write it like this. Minus 2 over 5, 2, 2 over 10. Okay, that's how we compute this. Checking. Yeah, it's correct. I guess I should turn this into a 1 over 5. Any comments or questions about this? Yes?
Normally, do you want us to stop by on the right-hand equation? Do you want us to stop there, or do you want us to simplify all the way?
I mean, probably it's better for you to be able to simplify all the way. But then again, if you think about it, how am I going to deduct points if you don't do it in the exam?
So like, there is a chance you could simplify wrong, so.
That is true, yes.
Okay.
Yes, clearly making a mistake here is a lot less dramatic than making a mistake here. If you sort of mess this up and divide it by y norm squared, whatever, that's a major problem, of course, compared to the calculation. Yeah. Yes.
If we don't have an orthogonal span of W,
Exactly.
we need to find one.
Yeah. Yeah.
Which line is y hat in the drawing?
The orthogonal projection. Yeah. Imagine this, okay? I have a point mass here, and I have a plane. And I'm taking a light source, sending it to infinity. It is a shadow here. Y hat is that shadow. Okay, very good. What your other colleague mentioned is the main point here. We'll transition to that. But the point, the reason why you get to do this, and this is a nice case, is because you're already given an orthogonal basis. Okay, so in order for this projection business to work, that is to say, in order to project this here, you first project it onto this, and then to this, and then you add them up. This has to be orthogonal to this. So if I had some other pair of vectors that spanned W, I could not have computed the orthogonal projection this way. So we need some way to compute an orthogonal basis. Hopefully, perhaps, you start with some basis, because we know at this point how to compute bases at large. But then, once you have a basis, you would want some sort of an algorithm that transforms it into an orthogonal basis. That's going to be Gram-Schmidt. Okay? So we're going to spend more time on that. I'm not done with this example. I want to say a couple more words. So Gram-Schmidt. I think that's how you write it. It's an algorithm that turns a basis into an orthogonal basis. Or if you want, you can also use it to turn whatever basis into an ONB, orthonormal basis. Okay? We're going to talk about that later. Any other questions about, yeah?
If you were to double check our answer by doing the answer times y, what would that give us? What would that output?
Answer times y?
Like if we were to double check our answer, like we would do the negative 2/5 to 1/5 times y equals, what would that output be?
Well, it's just going to give you something about this angle.
Okay.
You don't want to check it like that.
On the previous example, it gave us 2 times u. So will it give us something similar, like 2 times something?
No.
A factor?
No. Because in the previous example, you were projecting onto a one-dimensional space.
Oh, okay, I see.
Here, you have 2 components, so things are more complicated. But that's a good point. How do you check this? Well, one way to check it would be, perhaps, to say, well, if you take this and subtract from it this, you should get the component of y that is perpendicular to w. So to check this, what you can try doing is look at y minus y hat, which is this vector, the vector that takes y hat to y, and see if that is in fact perpendicular to w. Okay? That's what I wanted to say also, so let's do it here. I'll do it in blue. Right, so assuming that your calculations are correct, if you subtract y hat from y, you have a different vector. It should be perpendicular to w. So that's one way to check it. Check your calculations. So to check, is the remainder, right? So you sort of you projected y onto something else, but you have a discrepancy. Is this discrepancy perpendicular to w? You can check this. Okay? Your calculations are correct if and only if this is indeed an w perp. To check this, instead of dotting that discrepancy vector, y minus y hat, against an arbitrary vector in w, what you can check is you can check it against u1 and u2 separately. Okay. I'll do this in a second algebraically as well, just using the formulas, but let's just numerically check this. So this vector is, I'll first compute that actually. One, two, three minus that vector. Okay. So that's 7 over 5, 0, and then 14 over 5, which is to say 7 over 5 times 102. Okay? So I want to see if this guy is in the orthogonal complement, or the orthogonal complement of W. I think I'm going to erase this Gram-Schmidt, because we're not going to discuss it for now. So you see, instead of using this, you can just get rid of the scalar, because this scalar is not going to matter for the purposes of calculating orthogonality. So you can just check this. 102 against U1 is 102 against 2, 5, minus 1. 2, 0, minus 2, that's 0. Okay, 102 against U2 is 102 against minus 2, 1, 1. Minus 2, 0, plus 2, against 0. So you see this discrepancy vector, some scalar multiple of this, is indeed orthogonal to basis vectors. Therefore, this gives you that it's probably correct what you did. In this case, it tells you that you're definitely correct because the perpendicular is one-dimensional. But that's a good way to check. Okay. Any other comments or questions? Yes?
Why can we get rid of the scalar?
Because instead of looking at whether or not this guy, the actual discrepancy is perpendicular, I can scale it by whatever number. So in order for this to be perpendicular, say I look at half the same vector. It's again going to be in the same direction. So it's not going to change the angle. Okay, yeah. You don't have to, of course, but these are sort of shortcuts to fast calculations. Any other comments? Yeah.
If y is already perpendicular with w, are you just going to get 0 vector as y hat?
Yeah, very good. Yeah, in fact, I'll leave that to you. Take this vector, 102, compute orthogonal projection of it to W. You're going to get the 0 vector. Very good. Okay, I want to keep this because I want to come up with a formula similar to this. But the exercise is, take this, 102, orthogonally project onto W. Should give you 0 vector. Very good. Any other comments or questions? Yeah, sure. Now, I want to do two things here. I'm not done with this example. One of them is, well, I want to do the same thing, this calculation here, using only the formula. Okay, let's not worry about the numbers. Let's say y hat is this. I want to take this, subtract it from y, and see that that end result is going to be orthogonal to u1 and u2, purely because of algebraic reasons. And then I want to rearrange this expression into a square matrix. Okay. So let's do the first one first. So I'm just going to take this. Algebraically, I'm going to take this and dot it against u1, for instance. In fact, let's do it like this. I'll dot it against an arbitrary linear combination of u1 and u2 so that it's clear that this discrepancy vector is certainly orthogonal to any vector in W. So say you're dotting it against C1, U1 plus C2, U2. Okay. C1, C2 arbitrary scalars. I want to say that this is 0, purely based on the formulas. So first I'm going to expand. So C1, I can distribute this, because if I were to fix this vector, this dot product is linear here. Okay. But then for fixed vector in the second coordinate, dot product is linear in the first coordinate, so I can distribute once more. And then here I have plus C2 y against U2 minus C2 y hat against U2. Now I'm going to plug in the formula for y hat into this. Okay. I'm doing this for once because this kind of gets confusing, you see. So this vector itself, this formula, which itself has inner products, I'm going to plug in into an inner product. So this is, so I'm going to leave this as is and leave this as is also. But here I have now minus C1, this whole thing. This. Okay, in this expression, I just substituted, instead of y hat, this formula. Okay, and then I have one more with here, with this expression. Minus C2, y against U1, divided by U1 against U1, times U1, plus y against U2, divided by U2 against U2, times U2, and then U2. Okay? Now we expand everything. Once more. Okay, let's do this slowly at least once. The beauty of this inner product stuff is you can really calculate things rather fast. Minus. Right, so fixing this, I can distribute. This is a scalar, this is a vector. This is a scalar, this is a vector. So I'm going to distribute over sum, and then I'm going to take the scalars out. So this is this, and then like so, plus y against U2 divided by U2 against U2 times U2 against U1. I know that this kind of looks scary at first. I'm just doing it once just so that you have some exposure. These are the sort of standard calculations you end up needing to do in this business. C2 times, again, the same thing. And I'll tell you, this is not that bad, actually. Plus U2 against U2 times U2 against U2. Okay. Oh. Okay. So you have to, so the only thing that I would say here is you have to keep track of what is a vector, what is a scalar at all times. The point of inner products is it combines any two vectors and turns them into a scalar. And so you can take an inner product like this, put it inside this part or this part, whatever, so they sort of interact with each other. But the point of all this is this, okay? This is 0, because I know that u1 is perpendicular to u2. So this is going to cancel out. This is 0. This cancels out. u1 against u1 cancels out with this. u2 against u2 cancels out with this. But then this cancels out with this. And then this cancels out with this. So you get 0. So purely based on algebraic reasons, you start with this formula. That's the formula for orthogonal projection. Subtract it from y, whatever you're going to be left with is always going to be perpendicular automatically to the subspace you're projecting onto. Okay. And you can imagine if I had like a 50 billion dimensional subspace here, I would have, again, if I have an orthogonal basis, I can again just look at the sum with 50 billion summands, and the rule would work just the same. Yeah.
What real problem would actually have 50 billion dimensions?
Is there anyone who wants to answer this? AI, yeah. So pretty much any sort of technology you're using right now, without your consent, technically, is using this. You're using this, actually. Probably in like 2 years, you won't even be able to get gas for your car without eventually using this.
Yes, 50 billion dimensions.
Well, I mean, as you're approaching the station, GPS is going to tell the system that you're approaching, and it's going to give you just the highest price that you would pay for the gas. Very Black Mirror-like, but that's where we're going, ultimately. And in a sense, the point of discussing all this stuff, the point of linear algebra and stuff like that, is not that you're going to be better at doing this compared to a computer. It's just that you need to be aware as to what the magic is, so that you can say, I don't want this.
Yeah, like same way that programming is going to be in English in a few years, but you still need to know how everything works.
Supposedly, yes. Yeah. Very dire times ahead. Anyway. This shows in quantum mechanics too, by the way. So even for instance, quantum computing, you need things like this. And for quantum computing, technically, you need infinite dimensional spaces. So not even 50 billion dimensions is going to work. Anyway, any other comments or questions? I have a couple minutes. Let's try to come up with the matrix that corresponds to this proj sub W. And this is kind of the hint, okay? You see, this was an outer product. In the case of orthogonally projecting onto a line, I had one vector in the basis. I turned this, you see, into something like this. This scalar doesn't matter that much. But what I did was I looked into U transpose. Because U is n by 1, doing this product gives me n by n. And that's the linear transformation I need, because square matrices are linear transformations. So likewise, in higher dimensions too, I want to come up with an n by n that corresponds to proj sub W. Okay. So I'm going to take the formula and try to rearrange it. As a matrix vector product. Here's the formula again. Okay. Let's see. Well, I know I can write this as something like this, but is that what I want to do? Let me see. I'll do it like this, okay? You can sort of go ahead and store this or rewrite it in terms of this and stuff like that and try to add them up. But I think here's a slightly easier way to see this. I'm going to write this as 1 over u1 norm squared times something. Okay, plus 1 over u2 norm squared, y against u2 times u2. Now, I want to split these scalars, set them aside. One thing you can do, or one thing I can do is I can store them in a row vector. So I can write it like this. Hang on a minute. That's not what I want. This is probably going to take me a little bit more time. I think I'm going to continue doing this on Friday. So we need to come up with a square matrix that corresponds to projection onto W. We'll continue then. Thank you. All right, let's start. Good morning. I'm going to take attendance today again. So today we have a couple of things to do. Finally, I think it's time for us to discuss this Gram-Schmidt. There's something called QR factorization. At this point, you should expect some sort of a correspondence between doing things in linear algebra and there being a factorization in terms of matrix-matrix multiplication. That's generally the case. This is yet another instance of this. So for instance, we had row reduction. That turned into an LU type factorization. We're going to have Gram-Schmidt. That's going to be QR. There's a bunch of other ones. So singular or spectral decomposition is going to give you some sort of a diagonalization like this. So let's say Q, D, Q transpose. And then we're going to have a final version, something like this. So it's going to be, I guess what it's called is singular value decomposition, SVD. And it's going to give you a factorization like so. A equals P sigma Q transpose. Okay, so once you understand Gram-Schmidt, QR is going to be nothing but a way to sort of package whatever algorithm this is into a matrix-matrix product. Okay, now I want to do a couple of things. I'm still not done with this example we were looking into. We were looking into orthogonal projection in 3 dimensions onto a 2-dimensional subspace. Let me remind you the formula, or the numbers that we had already. So U1 is 2, 5, minus 1. U2 is minus 2, 1, 1. And Y is 1, 2, 3. Okay. We took W to be the span of U1 and U2. This was two-dimensional, and consequently, u1 and u2 was an orthogonal basis. Basis of y, w, sorry. Of w. What else did we do? I think we computed the orthogonal projection. We did some calculations. I'm going to remind you the formula in a second also. But ultimately, we computed y hat, which is the orthogonal projection of y onto w, to be this vector, minus 2 over 5, 2, and then 1 over 5. This we did last time. Okay. Now, what I want to do now is, well, I want to come up with a 3 by 3 that would correspond to this proj sub w, right? So proj sub w is supposed to be a linear transformation in and of itself. R3 to R3. And certainly it must be the case that it's a projection, that is to say, proj of proj should be the same thing as proj. So you see, this was the idempotence relationship. Any projection has to satisfy this, orthogonal projection. What I want is, I would like to be able to represent this linear transformation as a 3 by 3. Represent as a 3 by 3. You see, it's also good to be comfortable with this idea of thinking of a linear transformation as a transformation itself, not necessarily as a 3 by 3. In this case, we don't quite have, at least at this stage, an expression for proj sub w as a specific 3 by 3. But in principle, there should be one. Right? So what was the formula? Well, we use the fact that u1 and u2 are perpendicular to each other. Remind you. So when you say orthogonal, remember, this means not only are these two linearly independent and they span everything, but furthermore, in fact, the angle between them is 90 degrees. In other words, their inner product is 0. Oh, they're perpendicular. That's what that means. And so using this idea, we were able to come up with the formula for y hat. What did we say? Well, if I'm trying to project orthogonally onto a two-dimensional space, insofar as I have an orthogonal basis for that subspace, what I can do is I can first project onto this basis vector, then onto this basis vector, which I know from before. Then I can just add these two components up. That's what we did last time. So I'll try to draw, just so that we remember, something like this. Okay. This is 90 degrees. Their span is this W vector, W subspace. It's a plane. Okay. Y, 1, 2, 3, is some vector that sticks out. In principle, you don't need to start with a vector that sticks out. In this case, it just happens to be that way. So do it like this. I started like this, and I'm saying that this y hat orthogonal projection onto W okay, so this angle right here is 90 degrees. Okay, it was like this. In order to get that, what I can do is I can first take this y orthogonally projected onto the span of u1. I'm not going to draw this, but when you do this, you get this projection. And then I had another one like so. This is the orthogonal projection of y onto the second vector. And then y hat be obtained by adding this to this. That's how we computed y hat before. So well, one thing you can do is, well, we know how to represent this proj sub u1 as a 3 by 3. Namely, this is nothing but u1 normalized times u1 normalized transpose applied to y. Right, this was the outer product of u1 normalized by itself. And likewise, I can represent proj sub u2 as something similar. Okay. But then I can factor out the y and get one expression for proj sub w as a matrix. This was something that one of your colleagues mentioned at the end of last class. Certainly it is correct. It's not where I want to end up at, though. I'll just write it still. This plus this matrix okay, like so. Like so. Let's just check the dimensions real quick. u1 itself is 3 by 1. If I scale it by some scalar, that's still 3 by 1. If I take the transpose of it, that's 1 by 3. So this is 3 by 3. This also is 3 by 3. And if I were to, so I get to add two 3 by 3 matrices, and when I add them up, that's going to give me a 3 by 3 as well. Okay, so this makes perfect sense. And I can think of precisely this sum as a matrix representation for the orthogonal projection associated to W. Okay, that's one formula. In fact, I'll write it over there. Yeah, I'll write it like this. Let's just keep track of all the formulas we have so far. So you see, because I don't want to have this scalar in the denominator, which is the norm, if I were to just normalize the vector, I can just not write it. So if I'm trying to project onto a one-dimensional space with a unit basis vector, then this is nothing but y against u times u, or another way to think about it, is U transpose. Okay, these are two formulas that are true. More generally, if I have a subspace with orthonormal basis, okay, it could be 2, it could be 15, whatever, then all I'm going to do is I'm just going to add the corresponding one-dimensional orthogonal projections. If, let's say, u1, u2, dot, 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 uk, let's say, is an orthonormal basis for W, that is to say W is the span of these, then orthogonal projection onto W is the sum of these expressions. Okay, or I can just write it like so. But I'm going to do something slightly different now. I don't want to be first computing 2 or k n by n's and then adding them up. Somehow I want to directly transition to a matrix representation for W. Okay, so I'm going to do this. I go back to this expression and I'm going to rearrange certain terms. Okay, this, again, I'm using this. I can do it like that. In fact, I'll go one step beyond and I'll try to use this formula. It's slightly better. So this is y against u1 divided by u1 against u1 times u1 plus y against u2 divided by u2 against u2 times u2. Okay. Now, the denominator terms are u1 against u1. In other words, it's the same thing as u1 norm squared. I'll do this once slowly because it can get confusing. Okay. Now, this is u1 norm times u1 norm. One of those u1 norms I'm going to use to scale this vector. The other factor of u1 norm I'm going to put inside the inner product, which I can do because inner products are linear transformations or bilinear transformations. Okay. So this is the same thing as this. Okay. Now, this is a linear combination of u1 normalized, this vector, right? This is a scalar, this is a vector, and this 2 is a vector, and this 2 is a scalar. So this whole thing is a scalar, or it's a linear combination of this vector here and this vector here. In other words, I can think of this vector, this total vector, as the outcome of a matrix vector product. And I can change the orders of these as well. Write the dimension counts also. Okay. This vector is 3 by 1. 3 by 1, 3 by 1. Totally, this is 3 by 2. Okay. This is a bunch of vectors, but once you inner product, you get a scalar. This is a scalar. This is a scalar. So this is a 2 by 1. Okay. When you multiply, you're gonna get a 3 by 1. Okay. But also, this entry, okay, this inner product is nothing but this considered as a row multiplied by this. Because by definition, that's how you take the inner product of two vectors. Right? So same thing as this, which means I can factorize this also like this. See? This against y, this against y. In other words, this is the same thing as y left multiplied by the transpose of this. Again, let's look at the dimensions. This is the same thing as this. This is 3 by 2. Consequently, its transpose is 2 by 3, and y is a 3 by 1. Everything matches. Okay? But then, if that is the case, you see, this matrix multiplied by its transpose is a matrix representation for prod sub W. Okay? So let's call this matrix capital U. Okay? And this whole thing turns into U transpose times Y. Okay? In other words, prod sub W is this matrix, which looks very similar to this. In one dimensions, we had the vector outer producted with itself. In higher dimensions, you pretty much do the same thing. Really nice. I'll write it here. So if I have k normalized orthogonal vectors, well, put them in one matrix, okay? Now you have k columns. That's your capital U. Take the transpose of it, multiply them together. That's going to give you the that's going to give you another formula for proj. This is a really nice formula. All of these formulas work, okay? So whichever one you're most comfortable with, you want to start with that. But I think generally speaking, this ends up being the most convenient one, assuming that you have an ONB. Okay? This works insofar as you have an ONB. This is important. You need an ONB, orthonormal basis. If you have an orthonormal basis, put your basis vectors in one vector, in one matrix, take the transpose, take the product, you're going to get the matrix that corresponds to the projection. Okay? Any comments or questions? Now, you have to be careful with the order of the transpose. Okay? If you were to multiply U transpose U, that's going to give you 1 in this case, because U transpose U is nothing but U norm squared, but you started with 1. In higher dimensions, if you were to multiply U transpose U, you're going to get the identity matrix of whatever dimension. So it's not going to work. You have to be careful with in which direction you're taking the transpose. Okay. Any comments or questions about this?
Teacher?
Yeah.
Is the pro W unit vector? I mean, the vectors in this U1, U2, U2K.
Yes.
Oh, I see.
Orthonormal basis. Orthonormal basis means it's a basis. Any two vectors are orthogonal, and all of them are normalized. Okay, this is an important term. ONB, orthonormal basis. So UI, UJ is 0, UI is 1. In this case, I is not equal to j. Okay? You have to have an orthonormal basis. Okay? We haven't talked about how to come up with an orthonormal basis, but that's exactly Gram-Schmidt. Okay? We're going to get there in a second. Understand orthogonal projections first, though. This matrix representation and so on. What I want to do is I want to compute again this UU transpose and then see that indeed it matches with this calculation again. Okay. Again, I should remind you, orthogonal basis, okay, is not going to be sufficient. Okay. You have to normalize your vectors. Well, I mean, there's a version with orthogonal bases as well, but let's not get there. You can sort of try to come up with, you can sort of try to factorize these scalars into a matrix in between, which actually is significant, but maybe we'll discuss it later. Don't forget to normalize your vectors before looking at capital U. So, I'm just going to go ahead and directly compute this capital U, take its transpose, multiply, and then multiply that with y to get this result again, just to see that it works. So, we had done this calculation before, but let's do it again. Right? So U1 against U1 is 2, 5, minus 1 against 2, 5, minus 1. 4, 25 is 29, plus 1 is 30. U1 norm, therefore, is the square root of this, root 30. Okay. U2 against U2 is, well, minus 2, 1, 1, minus 2, 1, 1. That's 4 plus 5 plus 6, so that's 6. Its norm, therefore, is root 6. By the way, in this business, you're going to typically see square roots in the norms. Okay, that's going to happen typically, because we're typically looking at vectors with integer entries. When you look at the norm squared, you're going to have an integer. Typically, you're going to see sort of like the square root of an integer as a norm, at least in this class. Okay, so my capital U is u1 divided by u1 norm, u2 divided by u2 norm. Okay? So I'm going to take this vector, scale it by the reciprocal of this. That's the first column. The second column is this, minus 2 divided by root 6. 1 divided by root 6, 1 divided by root 6. Okay, that's my u. As you see, it's 3 by 2. Now to get the proj, we're not done. To get the proj, you need to multiply this by its transpose. So you look at this. So this is 2 over root 30, 5 over root 30, minus 1 over root 30, minus 2 over root 6, 1 over root 6, 1 over root 6, times this. Okay, then you multiply. So I'm going to get a 2 by 3 by 2, so it's going to be a 2 by 2 ultimately. Okay. I have 4 entries. Four plus 25 plus 1 is 30, and then I have root 30 twice, so that's a 1. Minus 4 plus 5 minus 1, 0. Minus 4 plus 1 minus 1, 0. 4, 5, 6, 1. Okay? That's the, yeah.
If you did it the other way, like u times u transpose,
Uh-huh.
and you do the 3 by 3, would it still be identity?
No. There's an issue here. Yes.
The transposers should, if you're trying to do like the factorization or to get the matrix, the transpose should be squared.
Yes. Okay. So this calculation is correct, but this is not the orthogonal projection. You're getting 2 by 2 identity. The dimension doesn't even match up. Okay. Orthogonal projection in this case should be 3 by 3. I told you, if you take it the other way around, you're going to always get identity. Okay. This is going to be automatic. This is not this. I mean, the calculation is correct, but this is not the proj. For proj, you need to do it the other way around, which is what your colleague is suggesting and your other colleague is also mentioning. Okay. So this is correct. But if you do a bunch of calculations, then ultimately you get this, and that's where you leave your calculation. I mean, it's nice that you calculated and verified something that was automatic, but you know, this is not the answer. I need the orthogonal projection. You got to do it the other way around. Let's do it. I'm going to look at this one. Okay. So first this, then it's transpose. Now you're going to get something more complicated. You want to get you're looking for something more complicated for orthogonal projections. Okay, like this. That's U. And then I'm going to take the transpose of it. Okay. Another way to think of this is this, okay? If this could work, well, I could just simplify the calculation a little bit. For instance, I could take out this 1 over root 3 in the first row, store it in a matrix on the left, essentially row reduction, and then just like calculate things much simpler. If that could work for orthogonal projections, I could have done it. But you see, this is the right thing that's going to give you the orthogonal projection, and you don't get to just pull out this 1 over root 30 in the first column to the left. You can store it in some matrix in between, but you cannot pull it out this way. So these scalars are really going to mess up this calculation, is what I'm trying to say. Consequently, you cannot just take the vectors you're given without normalizing them. If you were to put them into the matrix and take UU transpose, you're going to get something that is completely irrelevant ultimately. You need to orthogonalize, so they have to be perpendicular, they have to be normalized, okay? Okay, so let's do this product. 4 over 30, then plus 4 over 6, then 10 over 30 minus 2 over 6, then minus 2 over 30 minus 2 over 6, 10 over 30 what is it? Minus 2 over 6, 25 over 30, plus 1 over 6, minus 5 over 30, plus 1 over 6, minus 2 over 30, minus 2 over 6, minus 5 over 30, plus 1 over 6, and then finally I have 1 over 30 plus 1 over 6. Okay, consolidating, right? I can just simplify this just a little bit. I can just multiply this by 5 numerators and the denominators, so I have this. (20, 24) divided by 30, multiplied by 10, that's 0. Ah, is it? Yes, it's 0. Minus 2, minus 10, minus 12 over 30, that's 0. Because surprisingly, this is the same thing as this is the same thing as this, and this is the same thing as this. This is 30 over 30. This is minus 5, plus 5, that's 0, that's also 0. 1 plus 5 is 6 over 30. Okay. Finally, I can just simplify this just a little bit if you want. Divide everything by 6. That's 4 over 5, 0, minus 2 over 5, 0, 1, 0, minus 2 over 5, 0, 1 over 5. And that's your proj. Okay. I'll be done with this example once I just do this multiplication to get this result as well. But while we're here, let's note the structure. First of all, these zeros are sort of incidental. You're not going to get this shape in general, but you will always get symmetric. Okay? This proj is always going to be a symmetric transformation. Why is that? Well, because it is of the form UU transpose. Whenever you have UU transpose, no matter what the matrix is, AA transpose, let's say. Right, so if I were to take the transpose of this, when you distribute the transpose, you need to flip the orders. Okay, but A transpose is the same thing as A. So you're going to have this. Okay. So orthogonal projections are always going to be symmetric transformations. They're going to be equal to their transposes. Okay. So in this case, in principle, you're computing approximately n squared divided by 2 entries. So 5, maybe 6. So this lower triangular is going to be the same thing as the upper triangular part. Okay. So I want to take that matrix, multiply it by this to get hopefully this. I'm hoping that it's correct. So four over 5 minus 6 over 5. Okay, it's going good. Minus 2 over 5. That's 2. And minus 2 over 5, 0. Plus 1 over 5. Nice. Okay, it matches. So this was correct after all. Okay. So the formulas are over there. The simplest formula is in terms of inner products, and you use that inner product, the outcome of the inner product to scale your vector. But then you can think of this outer product for one dimension. For higher dimensions, you can just take the linear combinations of these, or as far as I'm concerned, the more convenient formula is you just sort of put these basis vectors into one big matrix, multiply it by its transpose like this. That's going to give you a square, and that's going to be your projection. You can do it in multiple ways. Okay. This format, this matrix format like this, ends up being more useful if you have multiple vectors you're trying to project onto the same thing. Because otherwise, you're going to have to sort of do this expansion multiple times and stuff. It's going to be nasty a little bit. Instead, just store your transformation in one matrix and then apply it to whatever matrix, whatever vector you need. Okay. Comments, questions? Okay. Now we can start talking about the main topic of this week, which is how do you even get an ONB? Well, you use this thing called Gram-Schmidt algorithm, but it's not anything any different than what we've done so far. Here's the idea. Gram-Schmidt starts with a basis, okay? Say you have a subspace And by doing, week 4 stuff or week 5 stuff, whatever, you are able to compute a basis for that subspace. Now, once you have a basis, Gram-Schmidt transforms it into an ONB or orthogonal basis. Okay. I have an inner product space, so vector space with inner product. Say it's finite dimensional. You don't need it, but for simplicity. Say W is a subspace of V. And say beta is a basis. You want to take ordered basis, technically, but ordered basis. Of W. Okay. What I want is this. I want another basis of W that is orthonormal let's say U, which is U1, U2, dot, 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 UK of W, and I'm going to introduce a new terminology with the same flag as beta. Same flag. Same. Okay. So that's a new term. Flag. Flag of a basis. The idea is this, okay? It's a very geometric idea. When you have an ordered basis like this, say beta, well, you want to think of it in a recursive fashion. You want to say, oh, I'm starting at the origin first, then I'm considering all of the positions I can reach using beta 1. That gives me a line, okay? On top of that, I start introducing the second basis vector. Now, that gives me a 2-dimensional thing. If I have a third vector, that gives me a 3-dimensional space, and so on. So flag of beta is 0-dimensional vector space that consists only of the origin. Then you have the span of beta 1. Then you have the span of beta 1, beta 2, and so on. And finally, in the last step, if you have all the basis vectors available, you have the whole thing. That's the flag. And why do they call this the flag? Because, you start with a 0-dimensional thing. This is just the origin. To it, you add a 1-dimensional thing. Okay? Then to it, you add a 2-dimensional thing, like so. And then you sort of turn that into a three-dimensional volume and so on. So this is this part. This part is this. This part is this. Okay. If you want to be more sort of algebraic, this really means span of U1 should be the same thing as span of beta 1. Span of U1, U2 should be the span of beta 1, beta 2, and so on. It's the same thing as saying having the same flag. Having the same flag is like faster way. It's faster to say. I prefer it, therefore. Okay, I don't want to push it. The idea is rather simple. We're just going to orthogonally project beta i's into previous vectors. But that's essentially it. And then, well, I think we'll do that on Monday. Thank you. Have a nice weekend.